Now let us take a look at an example where this model really gives us some benefit. So we can get some additional advantage out of using a linear mixed effects model. So this example is a real life example. I am going to use real life data when I use R to solve this example. This is about working with a tablet. Suppose here we have a tablet. Now when you have a tablet, for quality control purposes and other purposes, you have to figure out what is the total amount of active content that is present in the tablet. So how much really, what is the amount of the real drug which is present in it. So you cannot just find it out by measuring the tablet. So you have to do some chemical analysis. And there are various ways by which you can do this. Now two such are called HPLC method and NIR method. Now I do not really know what these two methods really are, but these are two chemical processes by which you can estimate, you can measure the amount of active ingredient inside a tablet. In this study, we want to compare between these two methods. So whether they give comparable results, etc., things like that. So for that, what I do is I take lots of tablets, so all at the same time, and then I split the tablet into two parts. So I just break it up into two equal halves and give one part to HPLC and the other part to NIR. As a result, I get certain measurements. Suppose I take 10 such tablets, so I send one half to NIR, another half to HPLC. So I get the various numbers. So I get, for example, from HPLC, I get the numbers which are these things. So Y11 to Y110. So 1 stands for measurement made by HPLC. Similarly, from NIR, I get the corresponding values Y21 to Y210. So the second index denotes the tablet which you have split. So from tablet 1, the first half goes to HPLC. The measurement is Y11. The second half of the same tablet goes to NIR and you get Y21. So the basic idea is we want to see whether on an average these are same as this, whether this is approximately same as that, this is approximately same as that. It is not that all these numbers are same or anything, so there are of course some random variation. We want to do that. So that is the problem that we want to address. Now the first thing that possibly comes to your mind when you think of this setup is the pair t-test. Now in the pair t-test, I hope you remember what the pair t-test is. We are basically assuming that the Y1j and Y2j's, these are jointly following some bivariate normal distribution. That is why we can now take the difference between Y1j and Y2j and say that that again follows a normal distribution with some variance, etc. And then we can carry out the t-test on those differences. That is the pair t-test, a very standard test. You have learned it already in your, I think, first year or second year. However, we are going to show that using a linear mixed effects model can actually improve upon this test under very similar assumption. The linear mixed effects model that we are going to use here is just the following. We already have two subscripts, Yij. So naturally we expect our linear model to be of the very familiar form, namely Yij is mu plus alpha I plus beta j plus epsilon ij. Notice that here I have written not beta j but bj. The reason is simple. I denotes the particular method. So HPLC or NIR, those are the methods that are of real importance. So I devote fixed effects for them. Now J stands for the effect of the tablet. I just picked some 10 random tablets. I am not interested in those specific 10 tablets. Anyway, they are broken and completely destroyed. They do not even exist now. So why should I ever care about those specific tablets? So the tablet effect is a random effect. That is why instead of writing beta j, I have written bj, plus of course we have our usual error term. Now what is the distributional assumption that I am going to put? Epsilon ij's IID normal 0 sigma square greater than 0, and their sigma square is unknown as usual. For bj's, I put the condition that normal 0 some tau square greater than 0, that is also unknown, and they are of course independent. So this model is very much similar to the assumption that we made for pair t-test, where I said that yi1 and y1j and y2j are jointly bivariate normal and they are independent between tablets. So this is very much similar to that. However, this captures one additional thing which was not captured by that pair t-test model, and this is the following thing. Let's compute the covariance between two things like this. I computed covariance between yij, I have written something slightly wrong here. I wanted to say covariance ij and I prime j. That is covariance between 1j and covariance 2j. So j remains the same, but the method is different. Naturally, you will expect that covariance is positive, right? It should be non-negative because it is just the two halves of the same tablet and you are measuring the activin gradient by two reasonable processes. So obviously, one indicates high value, the other should also indicate high value. So this covariance in this model is really non-negative. You can quickly check that will be actually equal to tau square. That is the covariance. Or I think tau square, yeah, it will be tau square. Because when you are taking 1 and 2, I is equal to 1 and I equal to 2, that epsilon will not have any contribution. They are two independent epsilons, but you will have the same bj that will contribute to the tau square term. So it will be non-negative. So that is one additional piece of information that we naturally have, which is incorporated in this model. But when we are using the pair t-test model, just bivariate normal, there we do not have any way of introducing that condition, that covariance between y1j and y2j is non-negative. That condition could not be incorporated in the pair t-test situation. In that sense, this technique takes care of more of the information that is available to us. I am not claiming that this is going to a big difference in the final outcome, but I am only saying even in this simple setup, linear effects model has some little advantage over such an established traditional technique.